All right, welcome back. So now we're going to continue from where we stopped. Okay, we are still on electromagnetic induction. Now we are going to be looking at a very important application of electromagnetic induction. In fact, this is actually very is a relevant application. Why? Because practically the electrical energy that is generated, okay, via this method is what we use today in for our domestic electrical energy supply. All right, so that is AC generator. So this same man Faraday that actually discovered electromagnetic induction actually went further, okay, to study on this particular phenomenon, and this particular device was actually discovered or was created, AC generator. Now, what is an AC generator? Now, an AC generator is a device, okay, or it's a device that actually converts mechanical energy to electrical energy. And we know very well that is exactly what happens in electromagnetic induction. But in this case, now the device is actually created in such a way that it will produce a substantial induced EMF that can actually power a load. Okay, so now without you know wasting time, let me actually uh, introduce this particular device. The diagram is actually showing here on the screen. AC generator. Okay, so there are two types of generator. We have both the AC generator and the DC generator. Okay, so they are all called dynamo. All right, dynamo. So they convert electrical and mechanical energy into electrical energy. So how is they constructed? Now a coil of wire. Let me use a different color. Okay, as you can see, in between two magnets, north south, okay, lies a coil of wire, right? So a cylindrical coil of wire, but just to represent the coil, I just use one loop, okay, of wire. Now, this coil of wire is actually positioned at an axis, or actually fixed, okay, to rotate about an axis. As you can see, this is the axis of rotation, the line here at the center of the coil. So now, what actually happens? Okay, since we know that anytime motion exists between a coil and magnetic flux, EMF will be induced. Okay, so this particular coil is actually fixed in such a way that it can rotate in a magnetic field. All right, and that's what happens here. So as the coil rotates in a magnetic field, of course, you know very well that the flux that's linking the coil will definitely change. Okay, and that will produce EMF. Now the question is, how do I get that EMF out to be used? Okay, how do I get it out? Since the coil is rotating, how do I connect a wire so that I'll be able to get the EMF out without twisting the wire? Now that is why you see in this particular diagram, okay, the coil is actually connected to an external load or external output via carbon brushes. This is a carbon brush. A carbon brush is not actually connected directly, okay, to the output. The output is taken via a two ring known as slip ring. Okay, as you can see here, these are two slip ring, the first slip ring and the second slip ring. All right. So of course, you know very well the EMF, that current that is actually generated by the coil, will be transferred to these two slip ring, and I need to get that current out for an output load. Okay. And for me to do that, I will have to now use a carbon brush, press it on the slip ring. Why? Because the slip ring will be rotating along with the coil. Okay. As the coil rotates, the slip ring rotates, and I will not want my output wire to rotate, because if my output wire rotates, it will twist. So all I just need to do, I need a carbon brush that will just press on that particular slip ring. So even if the slip ring rotates, okay, it will definitely transfer the current that it has generated to my output, of course, my output load. So uh, this is how an AC generator actually works. So what makes it an AC generator is what I will describe, okay, before I look at actually DC generator. Now, what makes it AC is because of the fact that the current or the EMF that is generated actually varies. Alternating, that's what AC means, alternating current. It varies, okay? because as the coil rotates, the EMF at each angle of rotation of the coil is actually varying. It's not steady, unlike what you have, okay, when you actually get an EMF from a battery. The EMF from a battery or a cell is steady, but that of a dynamo actually changes. So that is why it is called alternating current. So let me, before I describe that of DC, let me actually draw a diagram to show you how the EMF on alternating current varies. Okay, so this is actually going to be the graph. Okay, this is going to be the graph. So as the coil rotates, the voltage that is actually produced, all right, or the EMF, let me just use EMF, will actually change with time. So you're going to have, okay, a wave, okay, form of uh, graph. So at one point here, the EMF is maximum. Are you okay? Maximum is positively maximum positive voltage. At this point here, it is maximum negative voltage. So at one point, the EMF is positive. Okay. At one circle, the EMF is positive. This is the positive circle. This side depicts this positive circle, while this side actually depicts the negative circle. So that is why it is called an alternating current. Okay, because the EMF it produces actually varies with time, changes polarity with time. Okay, so at one point it's positive, at the other point of the circle is actually negative. Now, before I still come to the DC, let me, so we can actually generate a formula, right? So now, for us to be able to generate formula for the EMF generated by an AC generator, okay, we should know that the flux, okay, of this particular coil, the flux of this coil, we know that flux is always given as the flux density multiplied by the area. Okay. Now, since this coil, okay, is actually rotating, it has an angle. Definitely, all I need is the component of the flux that is horizontal. The component of the flux must be horizontal. Okay, please take note of that. We'll talk about the law. So the flux between these two magnets definitely must be horizontal. So if I want to actually uh, evaluate the flux I'm getting, I have to find the horizontal component. I know you treated when you treated vectors, for you to find the horizontal component of a vector quantity, because flux here, magnetic force is a vector quantity. Okay, so the horizontal component of magnetic flux is gonna be the flux density multiplied by the area, then of course cos. The cos theta now actually gives me that particular, multiplying this BA by cos theta, okay, actually convert the flux into its horizontal component, because I need the horizontal component of the flux. All right. So now let's actually proceed. So now this theta is actually the angle, because this is a circular motion, okay? The angle of the coil rotating in a circular, okay, in a circular motion, okay, rotating in a magnetic field. That is, it is exhibiting a circular motion or rotational motion, right? And you know that when in circular motion, if you have actually treated that before, this angular distance, or uh, the angular distance, actually, we use the theta here, please pardon me, theta, not the flux. The theta is the angular distance. The angular distance, okay, is always given as the angular velocity or angular frequency, okay, then multiply by time. Okay, why? Because angular frequency is always equal to the angular distance all over time. So for me to get angular distance, all I just need to do is to cross multiply. Okay, so that way now I can simply say that the flux in an AC generator is given as BA, okay, given as BA, then cos theta, which of course we know is omega. omega t. So that's the flux. Now, remember, it is this change of this flux now that will actually produce the EMF that we need. Okay, so let's now look at the change of the flux. Okay, so the change in the flux, you know very well that it's gonna be the change in flux, the differential change of the flux with respect to time. The flux, the time. That means invariably now, and don't forget that for EMF, okay, we definitely have to multiply by. So the EMF is always given as minus n multiplied by the change in flux times time. So that's going to be equal to minus n. So I'm going to differentiate this particular cos omega t. All right. I'm going to differentiate that. I'm going to differentiate cos on omega t. So if I should differentiate cos, if I should differentiate this entire expression, okay, I believe that you must have done differentiation before calculus, and differentiating with respect to time. This time here t. So of course, what's it gonna give me? This omega here is a constant, okay, so it's gonna come out. It's a coefficient. It's gonna come out as a constant when you do the differentiation. So I'm gonna have b, okay, or better still, the omega nw ba, then of course, then the cos now changes to sine omega t. This is the derivative of this, okay? So just in case you don't know what I did, just go and learn derivative. Anytime you differentiate cos, you always have sine, okay? Cos of every angle, you have the sine of the angle. Now happen that this angle now have a coefficient. So the coefficient after differentiating, okay, the coefficient will definitely come out as a constant, or the coefficient of the entire trigonometrical expression. Okay, but that's just by the way. So after differentiating this is exactly what I'll have. So, and that is of course equal to going to be equal to the EMF that is actually produced in the coil. So the EMF produced by AC generator is given by the formula. Let me write that again. EMF produced by an AC generator is given by the formula N, the number of turns of the coil of the generator, the angular frequency of the generator, the flux density of the generator multiplied by the area of the coil, then sine omega t. So write it down somewhere. We might need it later. All right. So that is it for an AC generator. So now let's now look at another diagram here. This is a diagram of DC generator. These two generators are all dynamo. Okay, they convert mechanical energy to electrical energy. But what's the difference between this? Okay, you know very well that for an AC generator, the EMF generated is always varying in direction. Okay, at one point is positive, at another point is negative. But here we want to get, okay, a positive, complete positive voltage. We don't want to have a negative voltage. So that is what we mean by DC generator. Okay, so now how do we actually construct a DC generator? How do we get arrive at DC generator? Simple. For you to convert AC generator to DC generator, all you just need to do is to replace the slip ring. Okay? So anytime you're being asked how do you actually convert AC generator to DC generator, it's simple. AC to DC is done when you actually press the slip ring of the AC. Okay, that slip ring where the carbon brush is actually connected. Okay, you replace it with slip ring, as you can see in this diagram. Slip ring. So this is where the I'm supposed to have slip ring, but it's being replaced with split ring. So what is the whole idea? So that when this coil actually rotates, okay, and changes polarity, then the slip ring would also change polarity. So that to make sure that at the end of it all, at the end of the day, what I will only have as my output voltage or the output EMF will only be positive. Okay, so the negative parts will not. Why? Because at the point where I want to get the coil want to give me negative voltage, then definitely the slip ring will actually change its polarity. So that will end up having this. This is the graph of DC generator only producing positive EMF with time. Okay, no negative EMF. All right, so please take note of this. Anytime you're being asked, how do you convert AC generator to DC? All you just need to do is to replace the slip ring. Okay, change the slip ring to, please pardon me, change the split ring to splits, to split ring, splits, slip ring to split ring. Then you have converted the AC generator to uh, DC generator. So I hope that is well understood. Okay, so we are gonna look at more in the next video. Okay, so see you in the next video. Thank you very much.